Number 1, for each of the following rules, write out the first 5 terms. So for 1a, we have a equals 2n plus 3. Now just a note, that is the same thing as a n in parentheses equals 2n plus 3. Alright, these two are interchangeable, they're just different ways of writing it. Alright, so I'm just going to use the first one. Alright, so the first term, I replace n with 1, and I get 5. The second term, replace the n with a 2. 2 times 2 is 4, 4 plus 3 is 7. Alright, third term, replace the n with a 3. 2 times 3 is 6. 6 plus 3 is 9. A 4. 2 times 4 is 8. 8 plus 3 is 11. And last one, a 5. 2 times 5 is 10. 10 plus 3 is 13. Okay? Now as you're going down, because you know the sequence is following a rule, when you get to the third one, you really could just start using the pattern, which is from here to here, you're adding 2, here to here, you're adding 2. Alright, so instead of calculating each step, you could just apply the rule if you want to. Right, so there's multiple ways you can do this. Alright, 1b. Alright, this time I'll use the other way of writing it. Right, but it means the same thing. I'm simply replacing the n with whichever term I'm trying to find. Alright, so the first term, replace the n with a 1. I get 3 times 1 equals 3. 3 minus 1 equals 2. Alright, replace the n with a 2. I get 3 times 2 is 6. 6 minus 1 equals 5. A 3. 3 times 3 is 9. 9 minus 1 is 8. And I can see the pattern happening here. I am adding 3 each time I go down a term. So if you want, you really don't need a calculator anymore. 8 plus 3, simply 11. And then the fifth term, add 3 to 11, you get 14. Alright, so as long as you can show that you establish that there is a pattern, right, going from here to here is the same thing, adding 3, then you can kind of do that a little quicker there. Alright, last one, 1c, we have 4n minus 2. Alright, so finding the first term, replace the n with a 1. 4 times 1 is 4. 4 minus 2 is 2. Now I can actually go even quicker because I know this is a rule, and this 4 right here is what we call the constant change of rate. Or it might be described as the constant difference, right? Meaning that each term is going to be increased by 4. So if you look at over here, the 2 is where the plus 2 comes from. The 3 plus 3. So if it's if n is being multiplied by 4, then you know that the next value is going to be increased by 4. Right? So I don't even need to solve at least 3. I can, after I get the first term, I can simply add 4 to all of my other values, and that makes getting the next terms a lot easier and a lot faster. Alright, so 2 plus 4 gives me 6, 6 plus 4 gives me 10, 10 plus 4 gives me 14, 14 plus 4 gives me 18. Alright, now there's no one way you have to do it. You can calculate them all, or you can calculate half and then use the pattern for the second half, or you can simply just start out using the pattern if you understand that this number right here represents a constant change. Okay, number 2, for each of the following sequences, write the next two terms and determine which of the sequences is an arithmetic sequence and what is the constant difference between the two. Alright, so first, if it has a constant difference, or in other words, constant change of rate, then it is automatically an arithmetic sequence. Alright, so really we just need to find out which ones are not. Alright, so I have the questions already written out over here. So the first one, 2a, so going from 3 to 6, we are adding 3, 6 to 9, also adding 3, 9 to 12, plus 3, 12, 15, plus 3. Okay, so we can confidently say that the constant rate of change, or constant difference, right, whichever way you want to say it, C equals positive 3. Alright, and the next two terms would be 18 and 21. Okay, because 15 plus 3 will give us 18, and then 18 plus 3 will give us 21. Next one, 2b, going from 7 to 15, we are adding 8, 15 to 21, we're adding 6, 21 and 28, we're adding 7. So the rate of change is not the same, so there is no constant rate of change or constant difference, so none, and therefore we are not able to predict what the next two terms are because it is not an arithmetic sequence. Right, so not an arithmetic sequence. Alright, moving on to the next one. -4 to -8, you are subtracting 4. -8 to -12, you're subtracting 4. And -12 to -16, subtract 4 again. Alright, so our constant rate of change is -4. And therefore our next term, we can predict it being -20, because -16 minus 4 is -20, and then -20 minus 4 give us -24. Alright, 2d, we go from 1 to 4, which is plus 3, 4 to 7, plus 3 again, 7 to 10, plus 3. Alright, so then our constant rate of change is positive 3. And then our next two terms, 10 plus 3 is 13, 13 plus 3 is 16. Alright, 2e, 3 to 8, we are plus 5, 8 to 13 plus 5, 13 to 18 plus 5. So the constant rate of change is positive 5. And then the next two terms, 18 plus 5 is 23. 23 plus 5 is 28. Last one, 2f. Going from 2 to 8, we are adding 6. 8 to 14, adding 6. 14 to 20, adding 6. 20 to 26, adding 6. So our constant rate of change is 6. And then our next term is 26 plus 6, which is 32. 32 plus 6 is 38. Alright, and then 2g wants us to determine a rule for the nth term for each of these sequences. Okay, so we can go back to each one, so starting with 2a, because we know that each term is being increased by 3, you can think of it as it's skip counting by 3. So when we skip count, if you think back all the way back to first or even second grade. When you skip count, you're not actually adding, you're skip counting because you are multiplying. All right, for example, if I want to find out what 3 times 4 is, and I don't have my times table memorized, I would be adding 3 4 separate times. I would plus 3, plus 3, plus 3, plus 3, and then I would get to 12. All right, so that's kind of what's happening over here. All right, so our equation or our function really is whatever n is, it's being multiplied by 3. All right, now anytime we come up with a equation or a rule, again, when they say rule or equation or function, it all means the same thing. All right, you need to plug the terms back, well, not the terms, plug the first term back and just double check if you are getting what you're supposed to get. So the first term, a1, is supposed to be 3, right? That's the first term, that's the second term, third, fourth, and so on and so forth. So a1 is supposed to be 3, so if we plug in 1, do we get 3? We do, so that's good. If you really want to be safe, plug in the next one. A2 is supposed to be 6, and we get 6, so that is good. Alright, so I feel pretty confident that 3n is our rule. Alright, 2b is not an arithmetic sequence, so there is no rule to be had. Alright, 2c, we have -4, so right away we can write -4 times n. Alright, and we'll go ahead and plug in the first sequence just to double check. Right, -4 times 1 will give me -4, and that is our first term, so that is correct. Alright, let's do another check just in case. A2, and again, I'm using 2 different ways of writing it. Either you can write it with the parentheses or you don't, whichever one makes more sense to you. Alright, -4 times 2 gives me -8. Second term is -8. That's good, so the equation or the rule is good. Alright, next one. I know it's gotta be multiplying by 3. Alright, and let's go ahead and do our check. If I input the first term, I get 3. However, our first term is supposed to be 1. Alright, so obviously that doesn't match up, but we can modify our initial equation to get 1. So after we plug in 1 multiplied by 3, we can subtract. So how do we go from 3 to 1? Well, we can subtract 2, and that will give us 1. Alright, so let me pick another term just in case, or just to see if it works out. So let's try the second term. Alright, so if you input 2, 3 times 2 is 6, 6 minus 2 equals 4, and the second term is 4, so that's good. Alright, if you want to be safe, try another one. 3 times 3 is 9, 9 minus 2 equals 7, third term is 7, that's good. Alright, so then I know that this rule, or I can confidently say that this rule is correct. Okay, so you have to be really careful, even though we know that n is being multiplied by 3 because the constant rate of change is 3, it doesn't always match out perfectly. So these two it did, this one it didn't. We had to do additional modification to the equation, or we had to subtract 2 to get our desired output. Right? So really this whole process is all about coming up with an equation, checking it, making changes to it, checking it again until it is perfect. All right, so if we move on to the next one, our constant rate of change is positive 5. So we start out with the equation 5 times n. All right, plug in the first term. we get 5. Well, first term is supposed to be 3, so to get 3 from 5, we need to subtract 2. So this is our new equation, and let's go ahead and plug in more terms just to double check. Alright, so we plug in the second term. We get 5 times 2 equals 10. 10 minus 2 equals 8. That is good. So, and you can go ahead and check more, but I know that that is good. Alright, and last one. Again, start out. Constant rate of change is 6. So we know it's 6 times n. But then now we gotta find out if we need to make any additional modifications to it. 6 times 1 gives me 6. I need a 2, so subtracting 4 will give me that 2. Right, and plug in the next term just to double check that it will work out. Alright, 6 times 2 equals 12. 12 minus 4 equals 8. 8 checks out. That is my rule. Alright, and you don't have to plug in 2. That's just, it's the next smallest number, so it would be easiest to calculate with. But you can plug in 3, 4, or 5 because we know what the third, fourth, and fifth term is, or really the sixth and seventh term. So if you want to, you can plug in. Say let's plug in the fifth term. Alright, so 1, 2, 3, 4, 5. So I'm supposed to get a 26. Let's see if we get a 26. 6 times 5 plus, minus 4. Alright, 6 times 5 is 30. 30 minus 4 equals 26. 26 checks out, so the equation works. Alright, moving on to number 3. It's more of the same thing. We need to write the next two terms and determine a rule for each sequence. Alright, so I have the sequence written out already. So, following the same steps, going from 5 to 10, I am adding 5. 10 to 15, I'm adding 5. 15 to 20, I'm adding 5. So that confirms that there is a constant rate of change, and that rate of change will give me 5 times n for my equation. Alright, and then I need to plug in some terms just to make sure that I get what I need. 5 times 1 equals 5, that checks out. Let's do another one just in case. 5 times 2 equals 10, so the second term needs to be 10. It is 10, so this rule is good. Alright, next one. 9 to 14, I'm adding 5. 14 to 19, I'm adding 5. 19 to 24, adding 5. So again, I am starting with 5 times n. But I know I'm going to have to make a modification to it because I just had the same one over here. But obviously these numbers do not match up with these. Alright, so I still need to plug in a term. And then, 1 is usually the easiest number to deal with, just to see how far off I am. Alright, so that equals to 5. I am 4 away from 9. Alright, so I need to add 4 to my equation or my rule to get me where I want to be. And then let's plug in another term just to double check. Alright, so 5 times 2 equals 10. 10 plus 4 is 14. So second term is 14, checks out. This is the equation I need. Alright, next one, 3C, 5 to 7, we're adding 2, 7 to 9, adding 2, 9 to 11, adding 2. Alright, so I start out with 2 times n. Alright, plug in a term, just to see how far away we are. Okay, we need to go from 2 to 5, so my adjustment would be to add 3. And let's go on and plug in the fourth term. Alright, let's see if we get 11. So 1, 2, 3, 4. The fourth term is supposed to be 11. So 2 times 4 equals 8. 8 plus 3 gives me 11. Checks out. equation's good. Alright, last one. 5 going to 9 is plus 4. 9 to 13 is plus 4. 13 to 17 is plus 4. So I start out with 4 times n. Right? And just to prove that you can use any term, let's start it with 2 this time. Alright. 4 times 2 gives me 8. I need to get to 9, so change my original equation to 4n plus 1 now. Right? And then we can even plug in the first term. Right? So it doesn't even have to go in order. I just need to make sure you keep track. If I'm using the first term, then I'm trying to get the first output, which is 5. Right, so 4 times 1 equals 4. 4 plus 1 gives me a 5, so that checks out. And there's my equation. Okay, number 4. Now we have a sequence of figures made up of toothpicks, and the toothpicks create the shape of a square. Alright, so now the sequence, they want it to be named with S. We've been using A just because it's the first letter of the alphabet, but S stands for square, so that's why it's picking S. And it represents the number of squares. Okay, so even though these figures are made up of toothpicks, that's not coming into play yet. You're simply counting the number of squares. So I copy down the pattern here. So the first term, and if you need to, you can write first term, second term, third term, and then fourth term. Alright, so the first term, there's 1 square. Second term, there's 1, 2, 3. Third term, there's 1, 2, 3, 4, 5. And again, if you need to, write out the numbers, that way you don't have to keep on counting. Alright, so each time I go from one term to the next, I am adding 2, it looks like. So I'm pretty confident that's my pattern. So if I go to the next term, I should have 7 squares. Right? If you want to, you can draw it out. I'm going to skip that because I really don't need to, because I know the pattern is plus 2. So then my next term, 5th term, would be 9. And I can keep on going if I want to, but right now that's all I need to confirm my pattern. Alright, so answering the question, for A, write out the first 5 terms of this sequence. Right, just so happens I already did that. Alright, so for A is simply 1, 3, 5, 7, and 9. Alright. For B, write a formula for S. Alright, so for B, I need to write a formula in terms of S. Well, actually, sorry, in terms of N. Right, so if our constant rate of change is 2, I know that it is going to at least have 2 times n in it. Alright, now let's go ahead and plug in a term just to double check. Alright, that gives me a 2. I am 1 more than 1, so my new modified equation needs to subtract 1. That will give me the desired output. And let's go ahead and plug in another term just to double check. Alright, so replace an n with a 2. 2 times 2 equals 4. 4 minus 1 equals 3. And the second term is 3, so that checks out. So that is my equation, or rule, or function. Alright. For C, write a sequence for the number of toothpicks T use at the end stage. Alright, so the sequence, you can hopefully there's some room, you left some room here. So now we need to count the number of toothpicks making up the figure, the square figure. So maybe I'll draw a line just to separate it. The first one, you got 1, 2, 3, 4 toothpicks. Alright, 4. Second one, we got 1, 2, 3, 4. 5, 6, 7, 8, 9, 10. Right, and if you maybe you can use a different color pen or pencil to differentiate the size you already counted. That might help. You can even use tick marks. So maybe you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Alright, now you can draw the next term and then count the toothpicks, or you can use the pattern to your advantage. Oops, looks like I missed a couple. 14, 15, 16. There you go. Almost messed that up. Alright, so the next term is 16, and the reason why I caught that is because I was going to say he can use the pattern to your advantage, and the pattern is plus 6. 4 going to 10, you are adding 6. Alright, so 10 to 16, adding 6. So I had 14 earlier, so I knew that wasn't right. So the next one, if I add 6 to 16, I should end up with 22. So if I did draw out all the squares and count the sides, I would get 22. And then going on to the next one, I should have 28. Alright, so just to double check what it's asking us to do, it wants us to write a sequence, right, use at the end stage. So you can write the actual sequence. We would have 4, 10, 16, 22, 28, then dot dot dot. Right? And if we want to come up with the rule, Sn equals change of rate is 6, so we will have 6n for sure, and then plug in a term just to check out how close we are. Alright, 6 times 1 equals 6. We are 2 more than what we need, so we need to subtract 2, and that should give us the right equation. 6 times 2 is 12. 12 minus 2 is 10. Second term is 10. Checks out. Alright, that is our rule. Okay, number 5. Similar question, but now the squares are arranged a little differently. Alright, so first one, 5a, write out the first 5 terms of this sequence. Alright, so you're counting the number of squares again. Alright, so just make it easier to see. Sequence term number 1, 2, 3, 4, and then 5. Alright, so the first one has 1 square. Second one has 1, 2, 3, 4. Third one has 1, 2, 3, 4, 5, 6, 7, 8, 9. Alright, now if I look at, now I want to kind of see if I have a pattern, so that way I have to draw the next one. If I go from 1 to 4, I am adding 3. Alright, 4 to 9, I'm adding 5. Okay, now that's the first time we've seen something like that. So let's go ahead and draw the next one just to check, since we had never done this one before. Let's have another way of getting the answer. So if I look visually, going from the first one to the second one to the third one, it would make sense that the fourth one would be a cube of 4 by 4. Alright, that would give me 16. Alright, and now the difference going from 9 to 16 would be 7. Alright, so even though the rate of change is changing, so that means it is not a constant, but there's still some kind of pattern to it. It looks like the first one is plus 3, second one's plus 5, third one's plus 7, and then we can probably confidently say the next one's going to be plus 9. So 9 plus 16 is 25. Alright, so even though we've never seen that before, we can still answer 5a. And again, 5a just wants us to write out the first 5 terms. So that's 1, 4, 9, 16, 25. Alright, 5b, write a formula for s. Now this is where it gets hard. Not sure how we're going to do that, because we've been dealing with patterns where the rate of change are constant, where they're the same. And that gives us a constant to multiply by. Now that it's different, we don't know what we can multiply it by. Well, this is where your just general pattern recognition kind of kicks in. All right, so let's look at the numbers a little bit. So first sequence, first term, we get 1. Second term, we get 4. 3, we get 9. 4, we get 16. So maybe there's a relationship between these two numbers. All right, because we already explored the relationship from this way, and there's no reason to explore the relationship here because they're just going in sequence. They're just adding 1 each time. So the only thing that's left is seeing if there's a pattern between the term number and then the outcome, the output. All right, so looks like if I add 2, I would get 4, but that doesn't work over here. 1 plus 2 is not 1, 3 plus 2 is not 9, so that doesn't work. All right, maybe we multiply by 2. If I multiply this number by 2, I get 4, but then again, it doesn't work over here. 1 times 2 is not 1, 3 times 2 is not 9. All right, so really, all I'm left with is squaring. If I square 2, I get 4. All right, and check over here. If I square 1, 1 times 1 is 1. Well, that works out. Let's see over here. 3 times 3, which is 3 squared, is 9. 4 squared is 16. 5 squared is 25. All right, so it looks like our pattern, whatever n is, you square it and you would get the next term in the sequence. All right. So unfortunately, there's not really a set rule or steps to follow to get that. You kind of just have to go through a little bit of trial and error. I mean, pattern recognition has a lot of trial and error involved. Right? When it's a more basic pattern like the ones we've been doing, you could follow certain guidelines to get it. But as it gets a little harder, then you kind of just have, it's kind of like solving a puzzle. There's really no one way to tackle it. You kind of just have to go at it at different angles until you get something that works. All right. So moving on, 5C. Write a sequence P for the number of toothpicks on the outside. So just the perimeter of the square. All right. That means we're only counting the toothpicks that make up the perimeter of each square. So this one we got 1, 2, 3, 4. So let's go ahead, just draw a line just to separate the two. All right, 4. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, and let's see if there's a pattern. 4 turning into 8, that is plus 4. 8 going to 12 is plus 4. So it would make sense that 12 going to the next number, I would plus 4, which would give me a 16. And let's just count just in case. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay? And then I'm pretty sure next one would be 20 over here. All right? So our sequence would be 4, 8, 12, 16, and then 20. All right, and the last question, 5D, just wants us to write a formula for that. All right, this is going back to what we've been doing previously a lot. The rate of change is constant. It's changing by 4 each time. All right, so we know that, and again, the sequence is called P now for perimeter. We know that we can multiply n by 4, the constant rate of change. All right, so let's go ahead and plug in the first term to see if we get it. All right, looks like it works. So let's plug in one more just to double check. 4 times 2 is 8. Second term is 8. That's good. All right, so we don't need to modify it anymore. That's the equation.